Swayam Prabha. Digital India. Educated India.
Welcome. Today we are going to discuss in continuation with our earlier lectures the defect in crystalline solids. Previously we have already discussed two types of defects, two groups of defects in fact. One was the point defects like vacancies, interstitials, Schottky defect, Frankel defect and so on. And then we have also discussed the one dimensional defects, that is, or in other words line defects, that like dislocations. We have also discussed different types of dislocations and their importance in describing or understanding the mechanical behavior of solids. Today we are going to discuss the third group of or third or fourth group of defects, which we call two dimensional and three dimensional defects. Earlier, as we have just mentioned, we have discussed the 0 dimension and 1 dimensional defects. Now we will be going to discuss the 2 and 3 dimensional defects. So, to start with the 2 dimensional defects, there are 3 types of 2 dimensional defects. The first one is called the twinning, the process of twinning, and by that process we actually generate defects like twin boundaries. Second one is grain boundaries, and the third one is stacking faults. Sometimes they are also called surface defects, because basically 2 dimension forms a surface. Well, the twinning, because all these defects are relative to the perfect lattice. This is a perfect lattice in which the atoms are arranged in a particular geometric fashion, and the horizontal lines are actually the planes. We can imagine one particular set of planes, and there is no defect in this particular case, either point defects or line defects or 2 dimensional defects in case of twinning. However, if there is a mechanical stress either internally generated or externally applied, depending on the nature of the crystal, its energetics and the energy required to form different kind of defects, a twinning may take place. This is what we call a twinning, that means a deformation, a kind of shear deformation. If we compare the earlier structure, the perfect lattice, and then goes to this twinned crystal or twin planes, we find a shear region where this part of the crystal remains intact. This also have the same orientation as it was originally present, and however, in between we have a region where the atoms are displaced. Atoms are displaced to some extent, not very large distances, but we will see the atoms are arranged or displaced in a particular proportionate manner. That means, this atom has moved smaller distance, this atom has moved from this distance to this larger distance, and so on, and this distance this particular atom has moved from its original position the largest distance, and they have a relationship between themselves. So, they again form a set of planes. Okay. They are not randomly distorted, they are not randomly displaced, but they displaced in such a manner they form a plane. So, this particular plane, which was a continuation plane with this, has now shifted downwards, and in between a plane has come up which is having a different orientation, but it remains as a plane. So, it is a kind of cooperative movement of a set of atoms under a shear stress, and they maintain certain orientation relationship. They are not randomly displaced, but they have a particular nature of displacement, so that they maintain a particular orientation among themselves, but that orientation is different from their original orientation. It also, one can look at this, if you look this boundary, either this boundary or this boundary, once again one can imagine a plane there, and if you look take the atoms across these particular boundaries, you will find this part of the boundary or this part of the plane is a mirror image of this plane. Okay. This plane is a mirror image of, or the deformed plane is a mirror image of the original image across this boundary. So, all the planes, all the set of planes here, parallel planes, forms a mirror image of themselves after the twinning has taken place. And similarly, this is also another boundary where this is a mirror image of this one. Okay. So, twin boundaries, these are called the twin boundaries, and the process is called twinning. So, the deformation, there is a displacement of this set of planes compared to its original position, and so there is a deformation, mechanical deformation, displacement of the atoms. So, there is a plastic deformation. So, this is also a plastic deformation, not an elastic deformation. So, this twinning is another mechanism, just like dislocation is a mechanism by which plastic deformation takes place. Twinning is also another deformation, it is a different mechanism by which a deformation plastic deformation takes place of a crystal, and these are called the twin boundaries, and they are basically planes, a set of vertical planes, and these also another plane. So, normally two different twin boundaries appear simultaneously. As a result, you have a mirror image of the original planes. So, this is what we call the twin boundary, and it takes place almost instantaneously. It is not a lot of time dependent process, it is basically takes place within a fraction of a second. So, this was the, once again if you can look at it, once again it is a perfect lattice, and then immediately it changes to a twinned region of the crystal. So, that is what we call it, twin boundary, and that is the definition. And there are crystals, going back, there are crystals in which twin boundaries are quite predominant, and particularly we have discussed earlier about the ferroelectric crystals. No, we will discuss later, frankly speaking we will discuss later. You will see these twin boundaries are quite predominant in some of the ferroelectric crystals, and many of the hexagonal kind of crystals, the twin boundaries or twin deformation is quite predominant. Well, that is, we will not discuss much about it, because maybe we will come across this kind of deformation at a later stage. I will just introduce you and define what is twin boundary. The next type of surface defects or two dimensional defect are known as the grain boundaries, because in any polycrystalline material it is a combination of a large number of single crystals, and these single crystals are oriented in a different directions. So, particularly until unless you take very special precautions, it is very difficult to prepare single crystals. Mostly ceramics are available in polycrystalline material, and therefore, the boundaries between two different single crystals within a solid, within a polycrystalline solid, it is actually called the grain boundaries. Okay. So, this is one grain, this is another grain, and that is another grain. So, you have boundaries, and these boundaries are called grain boundaries, and once again it is a two dimensional surface, and these boundaries, although we have drawn it in the form of a line, but they are actually they are surfaces, and they are not plane surfaces. Once one has to remember, they are not, unlike twin boundaries are plane surfaces. Here grain boundaries are very irregular shaped surfaces, depending on how the crystal has grown from its nucleation and by a nucleation and growth process, how the crystals have grown and finally collided with each other, forming a very irregular surface. So, these boundaries are called grain boundaries. This is one grain, this is another grain, and this is another grain. The characteristics of these grains are this grain having a particular orientation. For example, these are the these are the particular planes having orientation in this direction, but you can see the planes are oriented in a different direction, whereas in this there are other directions. So, the orientations in these crystals are different, and that is how the boundary is defined. So, if it is a continuation of the same orientation, then the boundary would not have been there. Because there is a change of orientation of the atomic arrangement of the crystals, that is why there is a boundary, and sometimes it is a combination of a large number of dislocations. A large number of assembly of a large number of dislocations can give rise to this kind of a boundary, and they are obviously high energy sites compared to the bulk of the crystal. These are the bulk of the crystal, or the grains. The grains have a lower energy, internal energy, whereas the grain boundaries are defective sites, and therefore they have a much larger energy per unit area. So, this is what we call grain boundary. They are quite prominent and predominant in any polycrystalline material, whether it is ceramics, metals, or any other alloy. This is a typical microstructure, a schematic of a typical microstructure of a polycrystalline ceramics. In particular, as we know, ceramics are always prepared from fine powders, and then the assembly of those powders or the compact powders are heated to high temperature, and then the chemical bonds are formed or sintering takes place, and finally there is a grain boundary formed. Okay. Now, to start with, ceramics, what we call the green compacts are porous, much larger porosity, and slowly as we increase the temperature or sinter or fire them at higher temperature, the porosity gets reduced, the grain to grain contact, solid to solid contacts develops, and finally you get a well developed grains, well developed single crystal grains. Okay. These are single crystal grains as you have seen earlier. But any polycrystalline material or particularly ceramics, the way we have prepared it, it is supposed to contain some amount of pores. So, the dark spots here are actually the pores, the voids. Okay. These are voids. There are two different types of voids, as you have seen, as you have marked here. These are the lines of the grain boundaries, and in the boundary junctions or triple points, which are called some triple points, the interboundary or intergranular pores are there. So, these are the retained pores or the remnant pores which could not be removed even after sintering within a limited scope of temperature and time. So, these are intergranular pores, they are relatively large pores, and normally these intergranular pores are open pores. What we call these open pores. Open pores means they are through and through pores, that means there is a permeability from one end of the surface to another end of the surface, it is open. So, if you try to push some gases or liquids, it can go through depending on the size. Okay. Whereas, there are another variety of pores which is called closed pores, or they are intragranular pores. That means, these pores are within the grains, not at the corner or junctions of the grain boundaries. So, these are within the grains, and these grains these pores are normally called closed pores. These are called closed pores, that means they are not through and through pores and impervious pores. They are closed from all the sides. So, these are the two different types of pores. We will see later that these pores are also one kind of defects, but otherwise these are the boundaries, these boundaries are the two dimensional defects in a polycrystalline material. Well, there are in addition to twin boundaries and grain boundaries, there is another type of defects, or what we call the stacking faults. We have seen earlier that the atomic arrangement or the atomic orders, the way the atoms are arranged is actually we can consider a stacking of different layers of atoms. We have seen close packed layers A, B, C, or A, B packing or stacking. Okay. So, that remembering that FCC lattice, for example, has a ABC stacking, whereas hexagonal close packed or HCP has AB stacking. But there it is possible that this stacking arrangement may not continue throughout the crystal. In some part of the crystal there may be some kind of a mismatch or some kind of a distortion or deviation from the stacking, and ABC stacking can change over to AB stacking. So, within the same crystal, it is not necessarily that all through you have the similar stacking. It may have a different kind of stacking, or the stacking sequence may change within a small region of the crystal, and that is what we call the stacking fault. Now, stacking fault may originate from different points of view, or it can originate from different reasons, but one of the reasons is what we call formation of partial dislocations. We have earlier discussed perfect dislocations having some Burgers vector, and that is the direction in which the atoms move, and the distance by which the atoms moves, that is defined as the Burgers vector. So, all dislocations are basically defined by a Burgers vector. So, this is here we have a line, as we have discussed earlier, that a dislocation is a line defect. So, this can be represented by a perfect line like this. So, this is a perfect dislocation, single dislocation having a Burgers vector, provided it is an edge dislocation, the Burgers vector is perpendicular to the direction or the tangent to that line. And in this case, it is an FCC lattice, that is the example we have taken, and Burgers vector in an FCC lattice is actually A by 2 1 on 0 direction. So, that is the close packed direction, and A is the lattice parameter. So, A by 2 1 0 direction is what we call the Burgers vector of the dislocation in an FCC lattice. Under certain situations it may happen this perfect dislocation, which is instead of a continuing like this, they have separated out into what we call the partial dislocations. Now, these partial dislocations actually arises because the displacement changes, the Burgers vectors get resolved in two different directions, one particular Burgers vector like B, which is now becomes B1 plus B2. So, this is the Burgers vector, this is like this, whereas this partial dislocations have a Burgers vector like this. Okay. This is the one B1 and this is B2. So, instead of the atoms moving from this position to this position according to this Burgers vector, the atoms will move, ultimately it will move to this position, but it will move via a different route. It will first move to this position and that is with a Burgers vector of B1, and then this moves to another final position from an intermediate position to this final position by a Burgers vector of B2. So, B becomes a combination of B1 and B2, although the ultimate result is same, but now because of the two different Burgers vector you have two partial dislocations, what we call the partial dislocations. When all the atoms are moved from this place to this place, it forms a one dislocation, and when the atoms moves from this place to this place, another dislocation. Okay. So, the line defect, the perfect dislocation has been resolved in two different dislocations. One is two different partial dislocations, and in between this region, between the space between these two regions, these also atomic arrangements are there, and this atomic arrangement is different from the rest of the crystals outside this boundary, and this is what we call and what we will see as a stacking fault. So, this because of this partial dislocation, because the atoms are moved from to a different position which it was not supposed to be under normal condition. So, this has a different stacking compared to the outside. Okay. So, this is the two Burgers vectors B1 and B2, A by 6 1 2 1 direction and A by 6 2 1 1 directions. Okay. So, these are the Miller indices of the directions. I hope you are aware of that. So, these are the Miller indices of the directions. So, this is 1 1 1 1 1 0 direction, instead it has been resolved in 1 2 1 direction and 2 1 1 directions. Okay. So, because there are two partial dislocations, the intervening space is actually have a different stacking than the original ABC stacking. Okay. So, this is what we call the stacking fault. So, a fault which spreads over a particular area. Well, this will be clear little in a different way, better way. Once again, this is a perfect lattice of 1 1 1 plane. These are the different layers of planes, and this may be, I think this will be clear in the next one like this. So, the perfect lattice has a ABC or on this direction, this is the perfect lattice here on this side. This is this part, you can see there is some deformations has taken place on this part of the crystal. On the left part of the crystal there are some changes, whereas this is the perfect crystal, and if you have noticed the stacking sequence, you will see there is ABC, 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 so FCC lattice. Now we have a two dislocations. If you have remember the way we define dislocation, there is a edge dislocation here, extra edge over there, there is another extra edge over there, and therefore, these are missing on this part of the crystal. Okay. As a result, you will see the stacking had changed. In this part of the crystal, the stacking had changed. Instead of ABC, ABC, which is on this side you have you can notice it is ABC, then AC, AC, and then again ABC. So, this part of the crystal, you say there is a stacking fault. Okay. So, the atoms are not placed in the right positions as in the perfect crystals, but some of the atoms are missing because of the formation of this edge dislocation, and therefore, this part of the crystal has a stacking fault, rest of the things have a perfect crystal. So, within a perfect crystal there is a stacking problem, or the stacking sequence gets changed, and therefore, we call it a stacking fault. So, this is the third type of two dimensional defect. Sometimes it is also called a volume defect, because it extends over some volume in a 3 dimension. It can extend to 3 dimensions. So, in some reference you will see stacking fault has been defined as a 2 dimension. In some other case you will find they have also defined it as 3 dimensional defects. So, these are the 3 different surface defects or 2 dimensional defects we have mentioned earlier. Next we come to 3 dimensional or volume defects, not surface defects, but volume defects. These are relatively simple to imagine. For example, voids and pores, okay. Inclusions or the second phase, okay. Of course, provided the dimensions, there is no particular critical dimension, but if the inclusions or the second phase, either it may be an impurity phase or it may be a designed second phase. If the volume percent or the size of those individual phase regions are very small, we can call them defects within a single phase region. Looking at the same microstructure, this is what we call void, because these pores are nothing but voids, okay. So, large voids are there. So, obviously, this is a 3 dimensional defect, whether it is a intergranular or intragranular, both of them have some volume, and therefore, these pores are always the 3 dimensional defects. Inclusion, this can also be a inclusion, a microstructure of this nature can also arise if there is, instead of pore is just in fact a, one can imagine as a pore as a second phase, compared to if this becomes the first phase, this becomes the second phase, a different material, a different kind of structure, but this is, in this case it is a void. Instead of that, this could be a different phase altogether, a different phase in the sense having different crystal structure, different composition and so on. So, depending on the overall composition, nominal composition of the material, there may be second phase. So, second phase of this nature, not pores, second phase of this distribution can also be called a 3 dimensional defect, okay. So, that is what we call about 3 dimensional defects, and the third one is what we call disorder structure. Disorder structure also is a 3 dimensional defect, and the example of a disorder structure, a simple example of this, it is of this nature. Let us say have a compound A and B, whether A are the one variety of atoms and B are the another variety of atoms, and it is a combination in which sizable fractions of A and B are present. Well, since it is an A B, obviously same number of A and same number of B will be present. If it is A to B, the ratio will be different, but in this case since 50-50 A and B. So, these are your A atoms and these are B atoms. Now, they are occupying the different sites, different lattice sites. Now, in this structure, if you look at on the left side, this is also AB, this is also AB, same compound, but the atomic arrangements are different. The relative positions of the A and B are different. Here we call it an ordered structure. All the A and B atoms are alternately placed, and that is an order arrangement of A and B atoms, because lattice sites may be indistinguishable, but the atoms are distinguishable. So, the way they are occupying the lattice sites, that determines what is the order, whether it is order state or in the disorder state. Here the A and B atoms are not occupied in regular lattice site, they are randomly distributed. Okay. So, this is an disorder. This is a disorder structure, disorder phenomena, where this is an order phenomena or order structure. So, this disorderedness is actually a defect, okay, compared to its normal thermodynamically equilibrium distribution, particularly at a higher temperature. The disorderedness increases and there is random distribution. So, this is also a kind of defect which actually occupies a particular volume. So, over the whole volume or a particular region of the solid, this kind of a disorderedness comes, and sometimes this disorder is also an order way. For example, in some kind of a layered structure material, we will see later on. In the layered structure material, some layers, some crystallographic layers or some atomic layers are actually disorder, others are order structures or remains the order. So, disorderedness may be restricted to a particular atomic planes or atomic volume or layers, two dimensional layers. Okay. So, that is also some kind of a disorder, but here we are considering the total volume. Now, we can define some order parameters that is basically a extent of order or disorderedness. S is called an order parameter, which is a measure of the extent of the ordering. R alpha is the fraction of alpha sites. Looking back to that structure, there are A atoms and B atoms, and also the lattice sites identified as alpha and beta sites. Okay. So, some are identified as alpha sites and some are identified as beta sites, particularly in an order structure. So, whether the alpha site is occupied normally, in a normal circumstances, alpha will be occupied by A and beta site will be occupied by B, but if that does not happen, then the order parameter comes in, and that is how it has been defined. S, the order parameter is R alpha. R alpha is the fraction of a site, fraction of sites, not A, I think it should be. 1 minute. Yeah, these are fraction of sites occupied by the right atoms, that is A. Alpha should have been occupied all the time A atoms, and beta should have been occupied by B atoms. So, and alpha, R alpha is the fraction of sites occupied by the right atoms or the A atoms, and W alpha is the fraction of alpha sites occupied by the wrong atoms. Okay, that is what it says. So, if R alpha is the right atoms and W alpha becomes the wrong atoms. So, for complete order, R alpha equal to R beta equal to 1, and for complete disorder, R alpha equal to R beta equal to half. Okay. Well, for a small degree of ordering, the temperature dependence of the ordering may be expressed in the following manner, which is a temperature dependence, and this is an exponential term, and there is a activation energy E d. So, the formation, so where E d is the energy required to exchange the positions of a pair of atoms. A goes to the B sides and B goes to the A sides, and energy requirement, just like your point defects formation of Frenkel defect or Frenkel pair or Schottky pair, you would always need certain activation energy. Similarly, this ED is the activation energy for the disorderedness. So, that is how this parameter or the extent of disorderedness is actually dependent on the temperature by an exponential term like this. It is normally assumed that the ED is proportional to the order parameter S. So, this ED is proportional to the order parameter which we have defined earlier, and the proportionality constant is a constant E0. So, there is a relationship between the order parameter and the temperature, and this order parameter remains more or less at one value, constant value, till a transition temperature reaches. This is what we call the transition temperature, where suddenly this order gets changed to disorder structure, or disorder structure comes back to the order structure. So, this is another kind of crystalline defect we crystalline defect we normally encounter in perfect crystals. So, that completes our discussion on the crystalline defects. We have earlier classes we have discussed about the point defects, next we have discussed about the line defects, and in today's class we have also discussed the two dimensional or the surface defects and the volume three dimensional defects, the volume defects. So, there are four varieties of crystalline defects: 0 dimension, 1 dimension, 2 dimension and 3 dimension. So, that completes our discussion. Each of them are of course different category different types of defects. Each category has different types. So, we have all discussed, and they have their influence. We have earlier seen how point defects influence the electrical properties, and then you have the line defects influence the mechanical properties. Also the two dimensional defect like twin defects, twinning related to the mechanical property, and then grain boundaries. Grain boundaries are integral part of polycrystalline materials, and they have a very important effect so far as various different properties are concerned. We will see whether it is mechanical property, whether it is electrical property, whether it is high temperature properties, all of them are controlled by this kind of defects. Okay. Having discussed all these and completed our discussion on crystal structures earlier, let us go to some question answer session at the end of this. Okay. I have taken few questions here and also discussed their answers given here. Some are descriptive questions, some couple of them are mathematical or numerical questions. The first question is, why do the cations in general, because we have seen earlier that it is the atomic arrangement of any oxide or compound actually contains cations and anions, right. So, the question is, why do the cations in general have smaller size than the anions? We have also seen why I am discussing this question. We have seen the size ratio has a very important role to play in determining the crystal structures. Okay. So, the answer to this question is very simple. The net positive charge, cations means positive charge, and the charge of the cations results from the removal of the outer orbital electrons, either the outer orbitals or the next inner orbital, particularly in transition metals or rare earths. So, either outermost or the next outermost orbital electrons are removed, whereas in anions are created by addition of extra electrons at the outer orbit. So, the ionic size of the cations in general is smaller than the anions. Okay. That is a normal thing, but there are maybe exceptions in there. We have seen in crystal structures that in some cases the cations and the anions more or less of the same size, but generally cations are smaller than the anions, and the reason is in one case you are removing the outer electrons, in another case you are actually adding the outer electrons. Of course, this is true for primarily for the ionic crystals. Okay. The second question is explain the importance of the ratio of the ionic radii in determining the crystal structures. That is what I was mentioning just now, because ionic radii of atoms or the ions, the cation or either the cations or the anions, that actually determines the exact arrangement of the atoms, and therefore, that leads to the symmetry and the various crystal systems and the description of the crystal structures. So, it is the coordination number. So, it also determines the coordination number of the cations and the anions that determines the crystal structure, right. This in turn is determined by the radius ratio of the cation to that of the anion. Okay. It is there is a very important role of the coordination number either of the cation or the anion in determining the crystallographic symmetry, and this coordination number is determined again by the radius ratio. What is the ratio of the crystal of the cation to that of the anion, okay. And therefore, ionic radii or the ionic size has a very important role to play in determining the crystal structures. I think the third question is how does the coordination number is determined by ionic radius ratio. It has an important role, no doubt, but how exactly it is determined, that is what you have to, one has to remember these limits. The answer to this question is the anions being larger in size forms the basic skeleton of the atomic arrangement. So, since atoms have the anions are larger, they actually form the skeleton. They come, they cannot come closer, too closer to to form the complete compact structures, but they touch each other earlier. If you are talking, if you consider the equilibrium distance of separation, then the anions will touch each other earlier than the cations. Okay. So, therefore, the anions being larger in size form the skeleton, okay, whereas cations even after the touching each other or coming to the closest packed position, they have some voids, they form a voids, and those voids are sufficient for the cations to be accommodated there, and that those are the interstitial sites. So, the exact coordination number or the exact polyhedra surrounding a cation is determined by the cation to anion ratio. This is RC by RA, and this is the coordination number. So, if this is between 0 and 0.225, this becomes a threefold coordination. If it is between 0.225 to 0.414, it forms fourfold coordination. Then it is still larger, that means the cation size is larger, relatively larger to the anion, then it goes to the eightfold, sixfold coordination, then eightfold coordination, and when it is exactly 1, both are equal, it forms a 12-fold coordination. Okay. So, that is the situation, and that is why the cation to anion ratio is so important for determination or consideration of crystal structures. The fourth question is so that the radius ratio range for the fourfold coordination of a cation is 0.225. That means, if it is between 0.225 and 0.414, that we have seen earlier, that we have listed earlier, but we have to justify why this number comes. this is the next question. How do you justify that if the RC by RA ratio is between 0.225 and 414, it becomes the tetrahedral coordination or the four-fold coordination, and that comes from the geometry, basic solid geometry. This is our next consideration. It is known that for thermodynamically stable configuration, there has to be a direct contact between the central cation and the surrounding anions, okay, forming a regular polyhedron. The cation must touch the surrounding polyhedron or surrounding anions. If it is smaller than the interstitial sites, it is not a stable site, it is not a stable configuration. It can be slightly larger, so that the anions can be pushed apart little bit, then also it is stable, but beyond certain point once again it is not stable, it goes to next higher coordination that we have discussed in our earlier classes. Okay. So, this is where we are trying to do, it is trying to consider or trying to mention here. It is known that the thermodynamically stable configuration, there for thermodynamically stable configuration, there has to be a direct contact between the central cation or the interstitial cation and the surrounding anions, forming a regular polyhedron. The lower limit for four-fold coordination corresponds to the radius ratio of a regular tetrahedron, radius ratio of, I think that of is missing, radius ratio of a regular tetrahedron of the anions and the cations at the interstitial position in contact with all the anions. So, it just touches the cations when the anions are in the tetrahedral configuration. On the other hand, the highest limit of the four-fold coordination corresponds to an octahedron of a similar nature. Okay. Then the geometries of these configurations are given below. I am just going to the next slide. So, from four-fold tetrahedron, that is the lower limit. Higher limit is when the anions are little pushed apart, but you have still the tetrahedron is valid, which is where the anions are not touching themselves. There is no contact between the anions, they are pushed apart because the cation is slightly larger, but the limit is until unless it goes to a regular octahedron. Okay. So, up to that point the four-fold coordination is stable. This is what a kind of cutaway view of the three-dimensional picture. Tetrahedron here is on the corners of each tetrahedron, each corner of the tetrahedron is occupied by an anion, and you have a small cation at the center of the octahedron of the tetrahedron. Okay. So, that is a cutaway view of the three-dimensional pyramidal structure, a tetrahedron. So, there are 4 atoms, 4 anions, and the center you have a small cation. So, we want to find out what is the critical size of this small cation here. Whereas, the other limit is the octahedron. This is the lower limit of the four-fold coordination, and the higher limit of the four-fold coordination is an octahedron, where you have a square bipyramid. That means, the one particular atom is not shown here, but there are 4 anions on the horizontal plane or the same plane, and then another anion on the top, another one on the bottom. So, that forms the 6 anions, and then that is the center of the bipyramid will have a small interstitial site which has to be occupied by a cation. Okay. So, these are the two three dimensional pictures. They are not drawn very regularly, but I hope the illustration is understandable. Now, here we are taking some sections. Here we are taking some sections. This is for the tetrahedron. Okay. Now, for the first, this is the base of the section, base of the pyramid, okay, on the tetrahedron, and this is a vertical plane, the vertical cartographic view or the vertical section of this same pyramid. Now, if RA is the radius of the anion here, these large ions, then this is of course 2 RA, this is touching along this line. So, at the base, and the distance between this and that is the center or the median of this regular isosceles triangle is 2 by 3, not isosceles triangle, it is equilateral triangle of course, 2 by root 3 RA. So, this distance is 2/3 of this distance. So, you will find this is 2 by root 3 RA, and if you take the vertical line, the details are given in the next slide. How it has been calculated is quite simple, the basic solid geometry consideration. This is your 2 by root 3 RA, this distance, and this is a vertical line, this is the vertical section, that is this is the apex, these are the two base and 3 base anions, and this is one of the base anions and that apex anions, the highest point. Okay. So, then this distance is 2 by 3rd RA, 2 by root 3 RA, and this is the height from this right angle triangle. One can find out this height is 2 by 2 into root 2 by root 3 RA, and this is 3/4 of this total distance. So, this height is actually root 3 by root 2 RA, 3/4 of this, and this is nothing but RC plus RA. RC is the diamond radius of the cation and this is the radius of the anion. So, this distance is equal to this one. So, in the this is what the details of the calculation for the tetrahedron, particularly the distance from the corner to the center of the triangle. Okay, center of the triangle means basically the median, along the median, and so this is already shown there in the diagram. Height of the tetrahedron will be this one from the right angle triangle, okay, the so called Pythagoras theorem, and the distance of the apex to the centroid is 3/4 of the height, and that is already shown there, and you will find this one from this one to this one, 3/4 of this value is this one, and then will be equal to RC by RA, and then once again looking at this values, we will see RC by RA equal to root 3 by root 2 minus 1, which is nothing but 0.225. Okay. So, the critical radius ratio for the tetrahedron is 0.225, and similarly of course, this calculation is much simpler, the consideration or the analysis is quite simple in this case. For the this is the base, this is the base of the bipyramid here. So, these are touching along this corner. Okay. If this is 2 RA, this will be equal to root 2 RA, and that will be equal to 2 RA plus RC, okay, this distance 2 R A plus R C is the this distance. Okay. So, so 2 R C by R A equal to root 2 into 2 R A, and that gives rise to R C by R A is root 2 minus 1, 0.414. So, the radius ratio limit for 4-fold coordination is 0.225 for the tetrahedron and 0.414 for the octahedron. Okay. Similarly, one can find out the other radius ratio limits which I presented earlier in connection with another question. So, we have derived this particular limit, one can very simply derive the other limits in the same consideration of the geometry. Okay. Okay. My last question which I want to discuss is related to the point defect. The question reads like this: the crystalline ferrous oxide FeXO, we have discussed earlier that it is a non-stoichiometric oxide which we can represent at FeXO is found to be have the lattice parameter of 430 pm is picometers or 4.3 angstroms, and a density of 5.72 gram per centimeter cube. What is the value of X? Okay. This again not a very difficult question to answer. It is known that FeXO crystallizes in sodium. This is very important. This is must be known. FeXO crystallizes in the sodium chloride rock salt type structure, and there are 4 molecules in a unit cell. This information must be known for most of the structures. Okay. How many? What is the crystal type of the crystal, and how many molecules are there in one unit cell? Okay. That is a very important requirement which must be remembered as much as possible. You will see in a spinel structure there are 8 molecules in a unit cell. Okay. There are many others where there are only one molecule per unit cell. So, the volume of the unit cell, because the lattice parameter has been given, and this is a cubic cell, cubic structure, FCC kind of structure. So, this is 430 cube, and that is nothing but 79.5 in 10 to the minus 24 centimeter cube. Okay, that was picometer, and this is, if you convert them, it will come to 10 to the minus 24 centimeter cube. Molecular weight FeXO. So, 56 is the atomic weight. So, 56x plus 16. Okay. And so, the weight of the unit cell is 4 multiplied by that into the Avogadro's number. So, that becomes gram. So, this is the weight of the unit cell, and that is the volume of the unit cell. So, density is simple. So, that is what is 5.72 equal to 224 x from here plus 64, 4 into 16, 64, and this equal to 6.02 into the power 23 into this, okay, 79.5 into 10 to the power 24 minus this. Okay. Well, I think there is a mistake over there. This 6.02 must go, no, here is a mistake. Here is a mistake. Okay. It should be divided by the Avogadro number. It is not multiplied by the Avogadro number. Okay. So, that then it becomes like this. Okay. So, anyway, if you can change this, it is a simple thing. If there is a mistake, you can rectify it, and it will be ultimately the x will come from this equation x will come as 0.936. 0.936. So, x becomes Fe 0.9360. So, that is how, that is in principle you can find out from the density and the lattice parameter what is the value of non-stoichiometry. Okay. I am sorry, there is a little mistake here, please correct it. Okay. So, that completes basically our discussion on the crystalline defects. Earlier we have discussed the crystal structures, and also we have discussed few questions and their respective answers. So, with this we come to the end of this discussion, and thank you very much for your attention.